sorts of neat features on here. So, big picture, the reason why we built this airplane is to prove that you can have vertical takeoff and landing and cruise efficient flight all on the same aircraft. And specifically, while we've not actually done the in-flight drag puller testing yet, we want to show that this is the most aerodynamically efficient VTOL aircraft in history in terms of lift to drag ratio. Some of the neat features on it, having lots of motors enables engine out. So you can lose an engine at any time, at any flight condition, and still continue to safely fly the airplane, even a tail motor. The distributed electric propulsion is really what enables this. If we look at all the VTOL planes from back in the 50s and 60s, two of their big shortcomings were they did not have good payload fraction, and they did not have sufficient control power. So distributed electric propulsion really enables fixes to those two problems. Being able to distribute the propulsion laterally and axially gives lots of control authority by varying the throttle commands on all those motors. And then also the power to weight ratio of electric motors is much better than combustion solution.
So it's about how much?
So these motors here have the power to weight ratio of a turbine, of like an airliner's power to weight of a large turbine engine.
So did you fly?
Yes. Oh, you've not seen the videos? So go to YouTube and go type in NASA Grease Lightning on YouTube.
What about the noise?
It kind of sounds like angry bees. Yeah.
Angry bees.
Yeah.
It buzzes like that.
But your friend here told me that you try to distribute the noise on a larger spectrum.
Yes.
Yes.
So if you were to consider, think of a general aviation airplane, you hear that.
Doppler effect, yes.
Yeah. But that's the blade passage frequency lining up on a very particular spectrum. If you were to operate each motor at a slightly different RPM, you're going to get that noise intensity over multiple frequency bands, and while the integral is still the same amount of energy, it's less perceptible to the ear because it's not all on that one blade passage frequency.
It's spread out.
You're spreading the harmonics.
Of course, but in a large rotor you have a spread of the distance of the Doppler between the front
well,
center
the Doppler
to
effect
the
is
edge.
a different topic.
Yes.
That's a different topic.
But the ear is really sensitive to specific.
Right. The ear picks up on the spikes.
Yes.
And if you spread that acoustical energy across multiple frequencies, Doppler effect is more amplitude change. If you spread it over different frequencies, it's less perceptible.
Of course,
Yeah.
but still the amount of energy integration
Yes,
is
the
the same.
integral is the same.
So
The integral
you
is the
didn't
same.
reduce the noise.
You reduce the human perception to the noise.
Okay, is the direction, any other tricks about the size of the rotor relative to the speed of the rotor?
Tip speed. So to
Tip
actually
speed.
reduce
So you reduce the
amplitude
tip.
of the noise, yeah. So the tip speed of this is like 450 feet per second.
450.
Which is-
relative to.
Most helicopters are like 750, 800 feet per second.
Okay.
And the acoustical energy is tip speed to the 5th power. So it's doing that as well. So significantly reducing the tip speed, which means you have to increase solidity to get the thrust back. So these propellers were actually intended to be two-bladed propellers, but we added solidity to make it, added a third blade to increase the solidity, which then means we can turn it slower to get the same thrust. And we ended up getting a custom winding of the motor to get a lower output RPM to reduce the noise. What's interesting is this airplane has a max takeoff weight of 62 pounds. Before we flew this, we were flying a 25-pound model to practice, and that had almost 700 foot per second tip speed, less than half the weight, and it was louder than this airplane.
What do you have there down in the center?
Oh, this bit? That's just a fairing. Oh, this?
Something there?
Oh, so this aircraft is a 50% scale model of a larger aircraft. The larger aircraft would have a SATCOM dish in it. So underneath here, on the larger view, this is just a subscale, would be a SATCOM dish with that directional antenna.
And what do you measure here? Just
This is
standard pitot?
beta, alpha, total pressure, and then there's static. Static ports are right here. So pitot, there's static.
Yes, I am. You know, it's just a lot of